and architecture stuff. I'm not a Linux hacker. I'm sort of pan-OS, if you like. I'm often in the position of having to present firmware interfaces to kernel audiences, which is always a bit of fun. But I am the only thing between you and beer, so gentle. Okay, so I've got security in the title, but security is really a hook for the presentation. It's not really a thing. But basic summary of what I want to talk about is, we come from an embedded background. Embedded / mobile is still the vast majority of what we do. But this embedded background is one where we've always assumed that the kernel is the only thing in control of power, and the OS is the only thing running. And because of that, interfaces can be really low level. So, Linux very often use interfaces at clock framework and regulator framework kind of level, as opposed to a give me performance level X kind of abstraction. And the reality is this low-level interfaces actually can be dangerous. I'm going to talk a little bit about some work that was done last year by University of Columbia that shows this. That's the security hook bit. But also, as some of the systems we do get increasingly larger, the reality is that there is lots of power management problems that just cannot be solved at the time granularity of the kernel. The firmware is there, and hardware is there, and sort of clock and voltage type interfaces, and even the way EAS approaches capacity might not be realistic, and you might have to think a little bit about that. ACPI has got one way of doing this, but for Linux, ACPI is very much in the realm of enterprise. So we've got some proposals of other standards type interfaces that we could try and do. We're trying to see if we standardize an interface where we could do something in DC, which gets us away from having a different solution for every single vendor. That in itself would be interesting. And I'm not here, by the way, standing as architecture recovery. Actually, I used to be a kernel guy in a different OS. So I'm not standing here saying, let the hardware's like this, get over it. It's more about discussion, given that systems are like that, what should be the right feedback signals? What can we do in future architecture revisions that make this easier and better? And that's the discussion I want to get. What have we learned from other architectures where these sorts of things already happen? It's a shame to see an ARM guy asking the info guys what's after that. Let's see what we can learn from that. Okay, so security is the first thing. So some of you might be aware of this work. I worked at the University of Columbia last year. They did a paper called ClkScrew, where they took an Nexus 6 device, and because the interfaces for power management are at the clock and regulator level, they actually let you put the platform into undervolted scenarios. You can actually ask for very high frequencies and very low voltages. And with this, they were actually able to do predictable failures. So essentially, predictably change the values of bits or read the values of bits, right? Or change execution patterns. And through that, they were able to read keys stored in trustzone, which is in our architecture a sort of our secret area, if you like, but also inject applications. So, and then I've got a couple of references there. So, although arguably from a kernel perspective, you could say, well, because the hacks here relied actually hack drivers in the kernel, you could say, well, they hacked the kernel, so all bets are gone anyway. But trustzone is where actual product secrets are stored for millions of products, right? And the SoC I'm talking about is in millions of products. And just as they managed to abuse a secure to non-secure boundary, you could use these sorts of techniques to use other boundaries, like kernel to hypervisor boundary, for example, type 2 hypervisor, for example. It should be possible to do this and maybe change PTE entries for the hypervisor itself, and change your stage 2 mapping, so when you write the end, you can read everything, for example. Those sorts of attacks would be in theory possible. And the problem here was that there's no mitigation for the power requests that are being done by the kernel. Give me this clock value, yeah, whatever. Give me this voltage value, yeah, whatever. I'll do whatever you say. But there's nothing in the middle saying, well, actually, that combination pairs the middle beyond me. beyond the limits of what my hardware can support reliably. Yeah, this is basically implemented. The other thing as well is, like I say, that in reality, again, power purposes is a perfect good answer. In reality, there are power management problems that you cannot solve in the kernel simply because the rate at which you need to adapt and change is too high, too fast for the kernel itself. The timing is a problem. There might be stuff you have to do in hardware. Stuff you might be able to do in firmware, so something is like that. And above that, yeah, you can definitely operate the kernel. But the other one is abstraction. The amount of controls that we're getting now go beyond just frequency. There might be other controls. And also the range and variety of voltage domain layouts, frequency domain layouts, also getting quite rich. And yeah, you could argue, try and comprehend every single possibility in the kernel and controlling the kernel, but it starts to get a little bit different. Whereas a bit like, utilization capping, right? An interface that's more, give me 20% of what you got, give me 80% of what you got. It's at least more abstract and you're able to cover a wide variety of platforms for that. With the consequences that you're talking to a firmware boundary or a controller boundary, and I know that that's caused issues in the past, and that's why I wanted to discuss that.
So you say certain frequencies, but the way
So you might see, for example, use of throttling or even selective use of throttling. That's an example. Also, the reality is for ARM SoCs, this is already happening, right? So it's not something that I'm kind of making up as a feature. It's going to happen more in the future. I can definitely tell you that. Just because of architectural stuff that we're adding, that makes kind of more interesting. But this is, I've anonymized it, obviously, but this is basically power in what's normalized to the max power this platform was consuming. On a platform where we were running, we were just running a power virus. So basically, we were running a dry stone thread on every single CPU. And they just observing it over time. And this was with intelligent, so IPA, disable and power allocation. Actually, not yet from Sasha, and the performance governor. So we're basically maxing this platform out, and we've disabled thermal management within the kernel. And what we observed is that the function was already coming in, and actually in a pretty crappy, frankly, bang bang kind of algorithm. It's cutting the power platform by cutting the things behind kernel's back already. And it's not going to tell you who this is, but this SoC is in millions of phones out there. That's all I'm saying.
That seems to me that most of the embedded systems on smartphone are using like that. Still, I think that we are almost all aware that kernel can't do everything.
Yeah.
The goal is that kernel should make some smart decision,
Mm-hmm.
and then the shorter the response time is, and the more dumb response you must do. And hardware and firmware are there to make sure that we will not burn the sub.
Yeah.
And that's what is happening there.
Exactly. Yeah.
Just because in this case the kernel is just dumb and stupid and doesn't do anything.
So there are things that are known to the kernel, and there are things that are known to the platform, and not necessarily, the knowledge is not necessarily in both places at the same time. So for example, the kernel knows what processes are running, what the priorities are, and so on.
Mm-hmm.
Whereas the platform knows the state of hardware at a given time.
Right.
And there may be no way to communicate, in real time between the two because of the timing and so on. So
True, and this is kind of part of what I've got some ties in between that. But really, where I'm getting to is what methods of communication should be, what makes sense. And actually, in a way, even in this kernel firmware, there's also kernel user stuff that we have been doing stuff like the whole sort of the same thing.
Oh yeah.
As every power management discussion then starts here and ends up going up the stack completely. But yeah, so I've got a couple of slides on example interfaces that had a go at this.
Sorry. What is Deerstone? The benchmark or a workload? Deerstone. The name is
Drystone.
Drystone. Yeah.
Oh, basically maxing out an integer math.
Okay.
It's misspelled, by the way, but it is Drystone. Yeah. Yeah, I can understand the question now. Yeah, that's meant to be Drystone. Yeah. It's just integer math. So ACPI has a go at this, and actually this is for Intel systems. It's going to be based on the API code for. But ACPI has a thing called collaborative process performance controls. It's got this notion of the OS and the firmware collaborating on performance control. But there, the interface is quite abstract. There, the interface is more of a bit like the utility interface. It's more on your plan over. It's like, give me 100%, give me 50%. Right? With some description also of what can be guaranteed, what's sustainable, what's not sustainable.
And the interrupt shift for sustainability changes.
Yeah, yeah. Unfortunately, ACPI is not that popular in certain parts of the ARM ecosystem. Obviously, good at that, and so we can't really use this everywhere. But yeah, one thing that's interesting about ACPI and thinking about feedback signals the kernel could use is CPPC actually does have a couple of feedback signals. It's got a couple of counters, and as you say, interrupts when sustainability changes. But one of the counters is what's the delivered performance at a. Basically, you can sort of figure out the average frequency that you're getting back, which the two counters. One of them counts at the rate at which the CPU is clocking, and the other one counts at the fixed rate. In theory, we could actually do very similar things with ARM platforms, even with ARM platforms today. We've come out with a spec for more the enterprise space called SCMI, where we're trying to cover a number of permanent use cases. So this goes beyond the performance thing. It's a very kind of generic slide, but I've got you'll all get a copy of this and go and find the spec there. I'm actually working on a second revision, so we're keen on feedback. But where we cover some of the device PM that you were talking about this morning, Raphael. We've got stuff for sensors, we've got stuff for performance management. And we've got the same kind of thing. One of the things that CPCC has, which is nice, is it breaks the abstraction on how you talk to the platform from the protocol, which says what performance I want. So you could, in theory, have different transports underneath the generic bit of the protocol bit. We've done exactly the same thing in SCMI. So we have the same kind of breakdown. And Sudeep has been upstreaming this, Rosie. Yeah. So, and I think it's not there yet, right? But it's. Oh, okay, cool. So particularly if you represent an RSSC vendor, I'd appreciate if you go look at it, because it'd be nice if we start to converge rather than having different solutions for different parts. And this is very generic and extensive. But then when we go back to feedback signals, one of the things we have been doing in the architecture is providing activity monitors. And this slide is from a debug architect, and I like it because one of the things we talked about earlier is that you can use performance monitors as one way of figuring out how many instructions you're retiring, for example, and that and then you could use that as your signal for utilization. The issue that we have is for our debug architecture, which gives you the performance monitoring. The debug guys have sort of taken that and they own that space, and they do not want to let go of that space, even though it makes a lot more sense to so we've added new counters to the architecture and to next generation CPUs. Stuff has been built now, which is not for diving in and doing debugging. It's just a constantly running counter. Right, so that's kind of the division between these two. So
can you write to them?
Only from a nice perspective, no.
Because in x86 you can actually write to a member.
Right.
And used to do that, and from years ago I get told that out. That makes an absolute giant mess of things. Now we just let them know.
Yeah, that's kind of what we are. Performance monitoring in itself as well. And that's why, for me to say, well, you know what, let's use the PNUs, because then we'd be able to use the existing CPUs and actually start to get these feedback signals in a generic way, even though you have to have functions for some CPU models. But basically, it would mean ripping the debug architecture quite significantly, as in perf architecture in Linux, quite significantly because of that waiting. You have to have some way of banking the values. And,
You can create in-kernel counters.
yeah, that was my, as a very 10,000 CPU architect, that was like, totally easy. But
I know we have APIs for that. The NMI watchdog, for example, runs an in-kernel counter. Debug that one, user space with them. Basically, have one that's down.
yeah, it might be worth the discussion. Because then we'd be able to do stuff on existing ones, and then in the future it gets a bit easier because we get architecture.
We have the system control to switch off the NMI watchdog. So the debug guys did that. They use that.
Yeah, I'm not surprised.
Yeah, ARM doesn't have that problem because there's no NMI.
Yeah, well, there's that. Of course.
Yeah, yeah, there isn't any like that. We have a spec called SDI, which basically gives you a software equivalent framework. You're asking about readability. You can actually, the highest exception level can rewrite them, but that's actually to implement the same restore logic. So that from the point of view of a hypervisor or a kernel, they are all constantly running. So yeah, in CPUs are being built now, so the 8.2 CPUs. There's implementation-specific versions of these counters appearing, and but from 8.4 they'll be available, and they map quite cleanly to the sorts of things that are in ACPI, and therefore quite cleanly to things. So, future, I think, we would be able to at least harmonize the two architectures to use a similar scheme. The other thing that was mentioned this morning, that when we did a little bit of experimentation with this. We were looking at ways of limiting frequency in pathologic situations that is fair than what that platform I showed you earlier did. So we did see situations where the frequency that you get might be on average lower than what you're requesting. And that did have an impact on the utilization signals, which then did have an impact on what the requested frequency, which then did have an impact on performance. So if we do start to look at using these counters, we need to figure out whether it's even worth it, just from that perspective. Because literally, you're like, when I use the counters, I get a lower defense score or whatever it might be than when I don't. Even though what I am of understanding of the frequency is actually more accurate. Or there might be places in the kernel where it does make a lot of sense to use, and places where it doesn't. So that's to be figured out. Yeah, that's kind of what I had. Kept it short and sweet. But yeah, the questions for you guys would be: are these the right feedback signals? Should we have other feedback signals? We've actually agonized a lot because in figuring out the firmware interface thing I talked about earlier, the SCMI, what sort of notifications we could have. If the platform decides to cut you for some reason, should you get an interrupt every time that happens, or should there be some kind of aggregation? And even if you have that information, what are you realistically going to do in the kernel with that information? I don't want to. We could imagine a million signals that we provide, but which ones are going to be? We're going to be here 2 years down the line and going, actually, we didn't ever use that, or that. Completely pointless. And shamelessly, also, I was curious as to from architectures where things like Turbo, for example, and if they have similar issues, what has been learned? Is any things that if you could start from scratch again, you would do different? That's my original question.
Maybe the first question is the pace at which you need to provide this information. I mean,
Yeah.
you speak about thermal mitigation, for example. Okay, so let's say that firmware or the hardware can provide the feedback saying, I'm capping the max quickly. But if it's doing that 1 millisecond every 10 milliseconds, for example, just keep it up, can't really do anything with that.
And yeah.
It's more interesting to say that 10% of the time, I don't have all the capacity. More than
some kind of aggregate.
It's half now, yeah.
Yeah.
That's really about, yeah,
or time window average.
exactly.
Yes.
So, first place, I particularly useful example.
Mhm.
It
Yeah.
is not architectural,
Mhm.
but it's very useful because power meter has a repair zone actually, and you can control, power count,
Right.
things. And
Yeah.
useful.
Yeah, so actually within, well, in kernel, with things like ACPI, we're looking at the load better packaging. And within SCMI, one of our, what we're thinking is an extra. And then I've got a way of making SCMI and CPI work together as well. So, and you might find that the transport defined by the ACPI spec and the SCMI spec are very well, not control of both. But ACPI has got parameter and packaging objects. So as far as I can see, the upstream supports that, right?
We don't use them. I mean, we use the RAPL
Yeah.
interface, as provided on top of them, through MSRs, and that's
Yeah.
it. Because, honestly, on Intel, ACPI is just, with those particular things, ACPI is just another layer of abstraction. It's completely, not necessary. It doesn't just says, oh, you have to use this register.
Mhm.
And
Well,
yeah, I know, I have to use it, right?
Yeah, I can understand if you have a very regularized hardware architecture, you can just go, oh, I'll just use the hardware architecture. For ARM, we didn't really force the industry to say we want to make a following registry that will that would be really hard.
I mean, I would say for OS, Intel went from, the days when we had these states in the kernel components to what we have now, the sort of black box.
Mhm.
From my perspective, it's unfortunate that all what's happening.
Well, this
And
thing,
so
yeah,
we get things are back, things are slow, and all we can at least log things, right? If there's a thermal issue, we'll say, okay, we're tapping, blah, 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 and that's useful.
Mhm.
So even when your question about what can the kernel do with the info, like logging is useful, even if that's all you do.
yeah,
Because when you get a report back from the field, that log is important.
yeah, that makes sense.
But definitely from a system integration perspective, or when you have something production, the workload, that's very useful.
At least I understand. Yeah,
If the kernel can do something about it, that's a different story. I mean, but at least you can, debug some issue when you feel due to that. Or even not only on the field, even when the system is being designed as well.
the one thing I've seen is kind of chicken bits, where
Yeah.
you saving certain firmware at the risk. So I mean, in one thing I found that this is often the kind of everybody thinks they know better kind of problem, right, that we have pervasive in the industry, right, where the firmware guys, hardware guys might go, well, actually we monitor a hell of a lot more possible counters that you possibly could in something like PSA. And so we think we know better. Whereas, on the kernel side, particularly when you have user side inputs for things like capital, whatever, well, we know better what's actually running. So, yeah, and then you end up in a.
That's why I don't know if it's actually possible to predict events, but it would be nice if we can provide the kernel information that allows to have proactive policy in kernel space. So something that say, okay, look, you are quite close to be capped
Yeah,
before it's actually
talked
happening.
about internally.
Kind of similar
Yeah.
in such a way that then the schedule or whatever the components can react to remain within a safe region.
Yeah,
that can
I
be-
think the issue there is, Steve, that you might not, that by the time you know, it's already kind of too late. So there's also people I got here thinking of thermal capping, but actually thermal capping is sort of the easy one. Power capping is the really hard one. Especially, so with vector extensions, for example, it's very similar to AVX, right? And that, as soon as you hit that territory, you're lighting up very large areas of CPU, right? So suddenly your power budget goes massively through the roof in literally just a few instructions. Right? There's no way you can react to that. I mean, actually, only the hardware route.
And we just use turbo buckets.
Yeah.
being able to CPPC request cross CPU, that's something we don't currently allow. So
Oh, I see. Be able to request performance in a different CPU to the one
Yeah.
requesting.
So when
Yeah.
we migrate a task, the migration might happen on the old or on a third
Yeah.
CPU.
Yeah.
And then you say you go run there. And in that context, it is very difficult to change frequency of that.
Yeah.
So then we need to encapsulate that information, send an IPI over, handle the IPI,
Yeah.
do the thing. It works, and it's better than I squared C.
Yeah, it is, yeah. But, yeah.
If you're looking at interfaces, that's one thing you might.
Yeah. That's one thing actually maybe we could even look at in the improving within the ACPI step, but I guess for you, Matt still likes to do anyway, so we don't have a way to actually get that in the spec.
Would you want to actually set
Well, with anything Intel, even when we had these days before HWP, it was all a hint. It's been microcontroller controlled for a very long time. And even HWP, it basically has the CPPC request fields inside an MSR. It's a machine register for the local CPU. That's how it is.
And the SCMI thing that we're doing embedded doesn't have that problem. Essentially, the CPU that you want to change is trying to work on. So you just go on the firmware. But that also assumes you have a mailbox, shared memory, and then something like. One of the things we're looking at for more embedded systems.
So it's a memory mapped MMIO or something?
It's very similar to the PCCC channel. It's shared memory with the controller. It's the idea. But for more deeply embedded platforms, which might not even have a controller, we have some thoughts on how you could do the same thing. I hesitate to say this, but the trustzone. Because we've kind of got nice ways now of separating other secrets and trustzone from this. So if this broke, it wouldn't necessarily reveal the secrets. Which would be more screen architecture. And then that would at least allow the kernel interfaces to basically stay the same, regardless of the type of platform you go for. But you have to trust one. That's the usual.
At the beginning, you mentioned that the fact that there was some attack based on overflow or underflow in the stuff. So with the CMI, we have a way to get some feedback. For example,
With SCMI, the idea is that the performance that you request is a performance level within the platform. You don't get to set the voltage independently of the. You get the information back, so it's someone who can know that a certain frequency crosses a certain voltage, but you can't actually individually set those.
And when your voltage domain is shared with other devices?
Well, it works. Yeah, that's a good question. It would have to abstract the voltage setting within the policy within.
So that would put constraints on the design of sharing a.
Oh, the constraints are there already.
Yeah, the constraints are there by the
You
hardware.
can't do physically impossible things.
No, but these are if you're sharing a clock domain or voltage domain with something other than a CPU. Don't do this.
Yeah, well,
That is something you'd have to mandate in order for this to work.
For some small embedded system,
it's
you
really
can't
hard.
say to someone because just adding one more regulator. Because
So
I agree that for a
I
large
tend
machine,
to,
you can put some constraint like that for big system, but
Yeah.
for small system where only one regulator is possible.
it is very hard. I mean, one way which is really manifest, when we first did the Vipsel, that was a premium feature. And so, say you will have a voltage domain for your CPUs and another one for your CPUs, so they're separate and from separately, was fine. But then it became a marketing feature, right? And so then everybody wanted to have it. And so now you do see more lower level SoCs, but you still try and say, hey, we've got the digital bit, but actually they're in the same way.
Data associates like starting as well, or something like that for API or stuff, and you have to have a device. Because there are dependencies like that. Like,
Okay, but none of those blocks or things are directly controlled.
oh no,
It's all in the
there aren't,
microcontroller.
but the dependencies still are there.
But
So,
don't we encourage this with dynamic a little bit also to share certain CPUs with uncore stuff, or not really?
Not really. I don't think the problem with dynamic changes in as much as that dynamic enables you to still have asynchrony per group of cores, right?
Yes.
So a dynamic, you could perfectly design a big little system that looks very, very similar to a big little system that you traditionally.
But if people want to save,
but if people want to, yeah,
Chinese,
but they
then-
could have saved clocks with the old one, right?
okay.
They could have saved in exactly the same way. They could have saved it.
And the feedback mechanism you just described when we ask for a performance state, is this mandatory that we always get it back, or is it something like?
Essentially, the firmware should always guarantee to the firmware should describe what levels are guaranteed, so that if you're within the realms of what's guaranteed, then you're okay. I think for things like EDF, for example, right, or real-time scheduling, that's going to be really important. Generally speaking, it should always strive to give you at least what you've requested. Right? And if it can't, you should get some kind of information to derive it. And the question is, what's the information you get back at what rate? Should it be time window? What makes sense?
I just remember that we talked about those path switching implementation, and then the feedback actually was not really mandatory. It was like that when we essentially request like a performance point, then it wasn't really clear that we essentially get the feedback back all the time.
Oh, you mean if you did it, try to do something in the fast path, frequency? Yeah, then that's the other topic. But I don't think we've actually done anything with that, right? I mean, actually, what you guys to tell me, but
Then in that case, I guess the solution was using the activity monitors.
But this is like
actually
activity
implement
monitor
this.
is like the
Yeah.
option number 3, right? We
Yeah.
have what we have currently with the K thread, and then there was the
Yes.
second option where we have already fast path, but it wasn't really clear that we get the feedback back all the time. But
no,
the
you wouldn't,
frequency-
unless so there's a few things we can do, right? So for future, for future or even for now, you could try and use PMUs or activity monitors when we come down the line. But with PMUs, take arguments with debug people. But at least that would give you something where you have a fair degree of accuracy and also good commonality with other architectures. It's kind of quite nice, in my opinion. The second thing you could do is you could say, well, the firmware has to provide me some stats and some shared memory location that I can just go read. That tells me, some maybe average sort of frequency or something like that. That would be another option. It'd look a little bit like the hardware counter, but it might not be as accurate. So we could definitely try and push towards architecting that. And actually, that would also work from an ACPI perspective, because we can describe the counters as a memory map location. I can see semantic changes that we need to clarify, but it might not be doable. The third option is that you don't have any. So you just have to assume that what you've asked for is what you got. So I think from a point of view of having counter-based abstractions to figure out what frequency was, average frequency was.
In one of the examples that you were saying before, like by looking at the stream of instructions, suddenly we discovered that there are certain events that and we have to be reactive. I was wondering, is there any kind of things that can be done offline, working at the tools level in such a way to maybe back annotate the code and detect this information and send proactive information? I mean, it's really a different domain.
Being in a university.
Yeah,
at an academic paper level, I totally buy it. And actually, there's
Do you
been plenty
know
of
about
papers
anything
written where they go and take the the compiled instruction stream and go, these are the annotated properties, and then through the loader they annotate the binary, and then a kernel reacts to that information. From a kind of business perspective of getting that, or even upstream perspective of getting that to actually fly, when you have to have tools, kernels, everybody agreeing, it's open crack, in my opinion. I'd love to do it, but
Hey, but do you know about researching in this direction?
There
or
has
it's
been
just
research in this direction, yeah, there has been. I can't put something specific now, but I've seen a couple of cases.
Company consider in the SCMI throw off some of the timing.
What? Oh, for timing attacks?
Yeah.
Yeah, actually, that is one way. That's actually one of the things that the ClkScrew paper suggested as one of the ways of preventing the attacks is to put a delay, or an arbitrary delay.
Because even if you've got an abstract scale, right, if you keep coming back to the same element.
So I've seen a lot of people refute that talking about the flux helps anything at all timing attacks. Because if you repeat the thing enough to defeat any variability you put into your code.
Actually, just do it more.
Yeah, just do it more.
And statistically,
or
you'll end up,
synchronize
That
against the
might
counter
happen,
loop if you have shared memory or anything at all.
Yeah, I mean, even in the ClkScrew thing, they I can't remember the exact percentage, but their attack consisted of repeating the attack, a million times, and they had something like 1 or 2% hit rate, but that was enough to do what they needed. So in your case, it's just been because we moved 10 times extra. That's fair enough. Because that attack actually relied very much on having a lot of precision as to when to change the OPP so that you're affecting a bit of code. That's going to say, for the one for injecting code, literally did the authentication of a certificate. So they managed to say, yeah, it is authentic, right? Because they hit the function at the right point to do that.
Yeah. I recently read a paper on checking SGX. That's the encryption thing.
Yeah.
So creative how they come up and reconstruct data.
Yeah. Very bright people doing horrible things to us. But actually, better that we know them because at least they publish them. Probably very bright people doing horrible things without telling anybody. Yeah. Cool. Any more comments for anyone? That's like my big deal of what.
No, they did first.
Cool. Thanks a lot.
Thank you.